So today we're going to tackle a really fundamental roadblock in physics. See, we actually know the basic laws that govern pretty much everything, but there's this one huge problem that stops us from predicting the future. We're going to explore that problem, the clever shortcut we invented to get around it, and, what happens when that shortcut just breaks.
Okay, let's dive right into this. At a really deep level, everything around us, the air, you, the device you're watching this on, it's all governed by a set of rules. The most famous one is probably Schrödinger's equation, and in theory, if we could just solve that equation for all the particles in a system, that's it. We'd be done. We could predict literally everything.
And that brings up the big question, right? If we have the universe's instruction manual, why is it so incredibly hard to read? Why can't we just plug in all the numbers and see what's going to happen next? Well, the problem isn't the rules themselves. It's the sheer scale of it all.
Take a look at this number. That's roughly how many particles, we're talking atoms and molecules, are in any object you can hold in your hand. That's a 1 with 23 zeros after it. It's an absolutely mind-boggling number. And that, right there, is where our perfect little prediction machine just grinds to a halt.
Yeah, the problem is trying to track 10 to the 23rd power particles is it's computationally impossible. Our very best supercomputers, the absolute beasts, they can barely handle around 40 particles. And here's the kicker. Even if we had some magic computer that could solve it, the answer would be a list of positions and velocities for every single particle. It'd be a mountain of data so gigantic it would give us zero actual human insight.
So to get any kind of useful understanding, physicists came up with this brilliant workaround about 150 years ago. Instead of getting totally bogged down in all those impossible details, they invented what we now call statistical physics.
The core idea here is beautiful in its simplicity. Just stop trying to track every single molecule. Forget about it. Instead, we track useful averages, things we can actually go out and measure, like the overall temperature or the pressure in a room. We basically trade impossible precision for practical, useful understanding.
And this brings us to two really important terms. You've got the microstates, that's the impossibly detailed picture of every single particle's position and speed, and then you have the macrostate. That's the big picture stuff we actually care about, like temperature. The key is that tons of different microstates can all add up to the exact same macrostate. Now, for this whole statistical trick to work, we have to make one crucial assumption. It's kind of the golden rule of the whole field, and it's called the ergodicity hypothesis. It basically says that a system left to its own devices isn't picky. Over time, it'll naturally wander through every possible arrangement, every microstate that its energy allows. This one simple idea is the bedrock of thermodynamics. Just think about pouring milk into coffee. Simple, right? At first, you see that distinct swirl. The system remembers exactly how you poured it. But because the system is ergodic, all those particles start mixing and exploring all their possible positions. Pretty soon, you just have a uniform light brown color. The system has reached equilibrium, and all memory of that initial swirl is completely gone, erased. So this idea that systems naturally thermalize, that they reach a uniform state and forget their past, that's a cornerstone of physics. But what if it isn't always true? What if there's a crack in this foundational rule? Well, it turns out you're probably looking right through a rule breaker as we speak. Window glass. The atoms inside are essentially frozen in place. They are not exploring all their possible configurations. On any timescale that matters to us humans, glass is just stuck. It's non-ergodic. It perfectly remembers the jumbled, disordered state it was in the moment it cooled. And this leads us to a really fascinating question. Glass is a classical system, but what about the quantum world? Could a quantum system get stuck? Could it hold on to the memory of how it started, not just for a little while, but forever? The answer, amazingly, is yes. And this is where things get really wild. We're entering a new frontier of physics, where breaking the rules leads to entirely new kinds of phenomena. This whole thing has a name: many-body localization. It describes a quantum system that just completely fails to thermalize. It gets stuck in whatever state it started in, and it just stays there, perfectly preserving the memory of its past forever. It never settles down into that uniform, boring equilibrium state. So how in the world does this happen? Well, the easiest way to picture it is to imagine the particles are moving through a really rugged landscape, with lots of deep valleys and super tall mountains. For a particle to move, it would have to go uphill or downhill, and that means gaining or losing energy.
But in an isolated quantum system, energy is conserved. You can't just create or destroy it. So the particles get trapped. They're localized. I mean, the difference here is just night and day. A standard, ergodic system acts like our cup of coffee. It explores everything, forgets its past, and settles down. But a localized system does the exact opposite. It gets permanently stuck, it remembers its past forever, and it never, ever settles down. It flat out breaks the textbook rules of statistical mechanics. And whenever you find a system that breaks such a fundamental rule, it means you kind of have to throw out the old rulebook. And in that new, empty space that opens up, you can find things that you previously thought were completely impossible. Think about it for a second. Our entire understanding of how big systems behave, of temperature, of entropy, it's all built on that one assumption of ergodicity. When that assumption turns out to be false, well, we are in totally new territory. The textbook is out the window. So what kinds of things are we finding in this new territory? Well, for starters, entirely new phases of matter that can exist at any temperature, not just way down your absolute zero. And maybe the most exciting part, we can create quantum systems that can store information perfectly without it ever leaking away. And that is a huge, huge deal for things like quantum computing. As the physicist Rahul Nandkishore puts it, when you break ergodicity, you are truly off the map. You are in here there be dragons territory. This isn't just about tweaking old theories. This is about discovering fundamentally new ways the universe can behave, ways the old rules told us just couldn't exist. It really makes you wonder, doesn't it? What other basic assumptions that we've held for centuries have tiny little cracks in them? And what other impossible physics is just waiting out there for us to discover? Thanks for joining me.